So now we're going to talk about section 4.1, rational functions. So rational functions are basically like ratios of polynomials. So rational functions, your suggested exercises are 3, 5, 7, 9, 11, and 13. So the main idea is, of course, rational function. And we've seen a few of these here and there so far in class. And then asymptotes. I mean, again, we've sort of talked about some of these. We've got horizontal, vertical, and then slant. Slant asymptotes are also called oblique asymptotes. We've also got holes that we're going to need to look at, and sketching rational functions. Your suggested examples to go through. So work through examples 1, 2, 4, and 6 in the book. So, a function f is a rational function if f of x equals g of x divided by h of x, where g of x and h of x are polynomials with g not 0 everywhere. Okay, so we can't have h not 0 everywhere. So we can't have, just something divided by 0, but h can have some zeros, and those zeros will just not be in the domain. The line x equals a, whoopsie-daisy, is a vertical asymptote if x minus a is a factor of h of x. This is kind of like, if x minus c is a factor of g of x, then c is a 0, right? That's because we did this from this previous section. Right, if x minus c is a factor of a polynomial, then it's a 0. Okay. Now, the line y equals c is a horizontal asymptote. This is different from a 0 horizontal asymptote. If f of x approaches c as x goes to either plus or minus infinity. So like as x gets past the graphing region, it's approaching this line, right? It's approaching this horizontal line. Finally, the line y equals ax plus b will be a slant or oblique asymptote if the graph of f of x approaches that line as x goes to. And when I write plus or minus infinity, I just mean, as it goes off to plus infinity or off to negative infinity. Now for rational expressions, rational functions like we're looking at in this section, it will be plus and minus infinity for both of these, but there are other rare types of functions out there that do different things. There are other types of functions out there that do different things, but we won't see them, or we'll see them very rarely in this class. Okay. This last thing occurs when the degree of g of x is exactly one more than the degree of h of x. All right, so you can find that by doing the long division using the division algorithm. You can find that. Finally, last thing, the function f has a hole or undefined point. Say isolated undefined point. If x minus d is a factor of both g and h, a hole at d. Okay, so we'll do an example that has some of these things, and we'll see kind of what we're talking about. So, quick example: sketch f of x equals x squared minus 3x plus 2 divided by x minus 2. Okay, solution. So the first thing that I want to do is I want to factor the numerator and the denominator. Now, typically in this class I'm going to give you factored forms, but if it's not factored, it's probably not factored for a reason. So let's factor it. So f of x equals, of course, x squared minus 3x plus 2 over x minus 2. When we factor the top, this is going to factor into x minus 2 times x, times x minus 1. And that's over x minus 2. Now, resist the urge to immediately cancel x minus 2 over x minus 2. We are going to cancel those. But what I see is I have a hole at x equals 2 because I have the factor on the top and the bottom. So in canceling those, I'm pointing out that there's a hole there, okay? Because x minus 2 on top and bottom. Okay, next we got a 0 at x equals 1, and that's because x minus 1 on top. All right, now let's do a quick sketch of this. So this essentially looks like the line y equals x minus 1. So y equals x minus 1. It's got a slope of 1 and a y-intercept of -1. So it's going to cross here and here. Got something like this. We're almost done, but you remember it's got a hole at x equals 2. So this is what f of x looks like, except at x equals 2, we need to draw a little circle there, meaning it's not defined when x equals 2. Okay? And this is how we indicate a hole. Now, if we were thinking ahead of time, we would have left a gap there. But if you forget and you draw through that little hole, that's fine. It's no big deal. Okay. So the next thing that I want to do is put this big theorem out for you. And this is called the horizontal asymptote theorem, or as I like to call it, the hat. Actually, I think the book calls it the theorem on horizontal asymptotes, but I like to call it the hat. Okay, so if f of x, let me give us a little bit more space here. If f of x equals, and I'm going to make a big nasty ratio here, so leave some space before you start writing stuff down. If it equals a sub n to the x times x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a1x plus a0 over b sub k x to the k plus b sub k minus 1 x to the k minus 1 plus dot 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 plus b1x plus b0. All right, so if this is our representation of f, 1, if n is less than k, then y equals 0 is a horizontal asymptote. 2. If n equals k, then y equals an over bn. Should probably make a cleaner y here. Is a horizontal asymptote. And 3, if n is greater than k, there is no horizontal asymptote. Now we saw from the previous slide, if n is exactly 1 more than k, then we'll have this slant or oblique asymptote. But if n is equal to k, then we're going to have a horizontal asymptote at an divided by bn. Now, this might be a little confusing, because if we look at the way that I've written the top, well, an makes sense. There's an. Where's bn? Well, there's a bk. So why did I write bn here? Well, I wrote bn here because this is in the case that n equals k. So if n equals k, then bk is bn. Okay, so that's just the ratio of the leading terms. That's how that works. So let's do a quick sketch of a graph of a function using the hat. Okay, sketch f of x equals 2x plus 2 over x squared minus 1. So you might want to pause the video and take a minute or two to try to factor the top and the bottom, see if you can figure out where the zeros and holes are, figure out where the vertical asymptotes are, figure out if it has a horizontal asymptote or not. I chose to yawn for some reason. All right, let's factor. So f of x equals, so 2x plus 2, x squared minus 1. Well, this factors 2 times x plus 1. The bottom factors as x minus 1 times x plus 1. And so I can factor I can cancel the x plus 1 off the top and the bottom. But before I do that, I want to note down that I have a hole. So hole at x equals -1. Now that I've written that down, it's safe for me to cancel this. I've also got a vertical asymptote at x equals +1, and that's from this x minus 1 term. Okay, and then what's the degree of the numerator? Degree of the top equals 1. Degree of the bottom equals 2. So this is my n, this is my k. So n is less than k. Let's go back to the hat. If n is less than k, y equals 0 is a horizontal asymptote. N is less than k implies y equals 0 is a horizontal asymptote. All right, so if you already know what asymptotes are and how they work, great. If you don't, that's also fine. We're going to take a little bit of time here and sketch out some asymptotes. Actually, why don't I, just for argument's sake, why don't I make this a little bit cleaner? All right, so I'm going to call this +1, and I'm going to call this -1. Oh dear, -1. So at -1, I know I've got a hole, right? There's a hole at x equals -1. I don't know what y is going to be there, so I just need to remember there's a hole there. Now for x equals 1, I've got a vertical asymptote, and I denote this with a dashed line through that x equals 1. Now I've got a horizontal asymptote at y equals 0, so that is indicated by a dashed line just around the x-axis there. And now what I want to do is I want to figure out where this graph is above or below the x-axis. Okay, so basically what I want to do is I want to look at this expression and do a sine chart. So the only key value on this expression is, the only factor is x minus 1. So my sine chart here, I've only got x minus 1, and that is going to be my total, but I'm just going to make the whole sine chart here. So we've got to the left of x minus 1, to the left of x equals 1 is going to be -infinity up to +1. To the right of x equals 1 is 1 to infinity. Now if you're wondering, like, wait a minute, Why is this a -1 and this is a +1? Again, I'm looking at this term, so there's something special happening here. That is, we've got a vertical asymptote, and this term is 0 precisely when x equals 1. So that's why we're splitting at 1 here and not at -1. So this term is negative when we're less than 1, and it's positive when we're greater than 1. Now if I multiply vertically, well, I just got one thing to multiply, so it's negative. If I multiply vertically, this column, only one thing, so it's positive, which means I know I'm up here to the left, and I know I'm down here to the right. I know I'm up here to the right and down here to the left. Okay. So the right-hand side, I know will look something like this. And before you say, like, well, how do you know it's going to look like that? Well, because I know that I'm somewhere up here, and I know that this has to eventually follow this line as x goes to +infinity. And I've got a vertical asymptote here, which means it's going to kind of approach this line. As the way this works is this gets closer and closer to being a vertical line as x gets closer and closer to that special value. And the function's not actually defined at x equals 1, which makes sense because that would be dividing by 0. But I know that it's positive on this side, and I know it's negative over here. So since it's negative over here, I've got something like this, and I just need to remember to leave a gap here at x equals -1. Okay, and this is a nice sketch of my graph. All right, I think that's good.